We move to the last speaker of the day, and that's going to be by Dr. Karthikeyan. He received his PhD in analytical chemistry from CUSAT India and did postdoc in US, Japan, and Singapore before moving to industry. So he has over 45 publications in peer-reviewed international journals, and also he owns 5 patents on water treatment technologies and applications to his credit. He has also served in the United Nations International Atomic Energy Agency for 2 years as analytical in analytical chemistry division. So his areas of expertise include analytical chemistry, food safety, environmental science, and advanced material testing, and laboratory quality management, ISO accreditations, and so on. And he has over 20 years of experience in various capacities, and he's currently the regional technical manager for Frontier Laboratories, Japan. And he extensively covers the business and technical support for Frontier. So welcome, Dr. Karthik. The floor is yours, and he'll be talking on PYGCMS applications for polymer processing and photodegradation studies.
Thank you, Prof. Vinu, for the kind introduction. Yeah, it's my pleasure to share about some additional applications on the polymer side to give some kind of provoking thoughts, how one can exploit the use of PYGCMS in your area of research or work. Okay, during my talk, I'll be giving some examples from polymer processing as well as some photo-oxidative degradation studies. Okay, so as I said, yeah, so I will cover two kind of application during my next 20-25 minutes. So let me start with the first application where I'm going to talk about the analysis of PAN, which is actually the polyacrylonitrile carbon fiber, okay, which is actually used in aerospace industries because of its unique characteristics like lightweight, high rigidity, and low linear expansion coefficient, high thermal resistance, and also the high thermal conductivity. So if you look at the manufacturing process of this PAN carbon fiber precursor, it starts from the monomer of acrylonitrile, go through the polymerization to form this PAN fiber. Then it goes to the second stage, calcination, which leads to the form of this carbon fiber precursor, which is used like a reinforced fibers for aircrafts building. Okay, so actually there is a publication available from one of our collaborator, like Professor Otani and Professor Suke, who has published about this stabilization mechanism in this macromolecules 190, like 1990. So let me take my laser pointer. Yeah, so definitely if somebody is interested to know more about it, they should refer to this publication. So I'm not a polymer scientist, so some of you may feel that what I'm saying here may not be making sense. So please refer back to us. We will try to address that. Okay. So when you do a pyrolysis of this PAN carbon fiber, it can go to 3 different kind of reactions. Okay. So one is the main reaction, what we intend to do through this cyclization, through this calcination, and it can also see the side reaction of the unreacted polyacrylonitrile polymer, which will form show the decomposition products of monomer, dimer, and trimer. Also, there is during this cyclization, there's a condensation process happening, so which will also release some hydrogen cyanide and ammonia. So our idea is to look at some of this product distribution and try to understand the stabilization mechanism and how one can use the PYGCMS to optimize this stabilization process or the manufacturing process. The first data that I'm sharing here is coming from this evolved gas analysis. Okay, so here we are trying to show the relation between this EGA thermogram versus the peak area and apex temperature of the different precursors, which are stabilized at different duration. So starting from the untreated one at 0 hour versus like 0.2 hours and 2 hours, 4 hours and 20 hours and so on. So what you can see from this evolved gas analysis thermogram, the peak shape is like when it is untreated, it shows like a through two kind of peaks, which getting reduced during the stabilization, and from like 2 hours onwards you can see it is appearing as a single peak. So this is something you will see even in TGA also, but it is not really giving much information other than this peak shape changes and also the temperature changes. Okay, so again this data has been drawn in a different kind of graph, where we can see the normalized peak area reduction, okay, is one thing. Another one is the apex temperature. So if you see the apex temperature at the beginning, it's around like 300 plus, then you can see it is going up when we have the stabilization duration is longer. Okay, so but as I said, this is only giving the temperature profile, also the peak shape of this thermogram. But as you know, our EGA even can help you to get the average mass spectrum, from which even you can look at some of the chemistry information as well. But we also recommend to consider this flash pyrolysis analysis of these materials. Again, as I said during my previous one of the slide, the reaction mechanism. So if it does not have cyclization, then you will see the formation of monomer dimer trimer. And what you can see here, compared to the untreated one, where the dimer and trimer peaks are prominent, that is being getting reduced as the stabilization time increases. And you can see by 2 hours it's almost disappeared. That means by 2 hours of this stabilization, you can assume that there is no real pan. Most of them are really undergone this cyclization and form this ladder like structure. Okay, so this is one way one can really use this PY-GCMS to look at the process optimization. Another side reaction that I mentioned also shows the release of this hydrogen cyanide and ammonia. So we try to measure these two during these different samples. Again, you can see the increase in the formation of, because when the cyclization takes place and during this second step of this condensation, that starts releasing this hydrogen cyanide and ammonia. So you can see as the stabilization time increases, you see the increasing trend of these two, but after 2 hours it is also reducing. So that is again due to some cessation. That means a longer hours is something is not recommended. So 2 hours is something considered optimum for this stabilization of this carbon fiber to make this cyclic structure. Okay, this is one type of approach where you can use the EGA and PY-GCMS, the flash pyrolysis, to help optimizing the polymer processing. Now, the same material has got another unique kind of stereo irregularity that also can affect the material performance in terms of the mechanical properties. So in ideal way, one is looking for a cyclization to form a ladder-like structure. But if your carbon fiber is of a different isomer, that may not form what this ladder-like structure. So now the question, are we able to use the PY-GCMS to do this differentiation of the stereo irregularity? So that is what we are trying to demonstrate through this application. So in this case, we have taken the samples of this polymer with a different stabilization time in air. Okay, like starting like 215 for certain duration, like 20 minutes, which is kept constant for all cases. Then we varied that stabilization time at 235. So what we know, looking at the decomposition products of this carbon fiber, so we get the residual pan, okay, the unreacted monomer. Then also you will see the kind of the monomer, dimer, and trimer, and these do not tell anything about the cyclic structure. So we have to look for an additional peak, that is actually a tetramer, that may show a different triplet that can be used for differentiating these two different isomers. So that is what I'm going to show it in subsequent slides. Okay, so is one of the sample number 5. So okay, when you see this, as I said, this monomer, dimer, trimer is actually interprets the data of the remaining polyacrylonitrile polymer. But the tetramer is what we are interested to see the stereo irregularity. Okay, so to make really the isotactic structure, the ladder-like structure, we have to see the formation of meso okay, tactic, and whereas the other kind of isomer will produce this racemo. So based on this, the individual peaks and the total peak area, one can really calculate this kind of the portion that favors the ladder-like structure. Okay, so we have analyzed this with all like different samples of different conditions, and we can see the around 120 degree we are able to see in favor of this meso isomer uh, that leads this ladder like structure formation. So we have actually taken the sample from the open market, okay, of 3 different category, where they have labeled this isotactic as like a 70%, 50%, and 28%. So as I said before, if the isotactic is the main isomer, then you have to see the bigger, larger peak area for the A, and versus the other one for the reso for this B. So based on difference one can calculate. So we have taken these 3 samples which are undergone the flash pyrolysis, and collected data has been calculated based on the intensity of peak A over like total peak intensity of the tetramers like A and B, and we can clearly differentiate. Okay, as I said, P1 should favor this the meso isomer. So where we can see the 70% is showing that means the peak area for the first peak is larger than the second peak. So similarly for the second sample, and so it is another kind of application where PYGCMS can be used for stereo regularity studies of different polymers. Okay. Now I move on to the second application. This is again on the processing also. As you know, in 3D printing industry or applications, one we use a photopolymer. The photopolymer, basically you have the polymer and then photo initiator that are blended, and after your 3D application or printing or like, then you basically expose them to the light source for curing. After that, this will remain stable for longer duration. Okay, so this is what one preferably want to see in terms of the material durability and also the performance. But now how we can use a PYGCMS to really understand this mechanism is what I'm going to explain or demonstrate with this application. Okay, as we know the photo curing reaction, so you have this photo initiator. When they get exposed to the photo light, so they usually form these free radicals, and these free radicals react with the polymer, this polyethylene glycol, and they actually form these cross-link and network structures. Okay, so based on this networking structure, one can really assess the durability of this material. That means one have to see more of this cross-linked network structure to increase the stability or the durability of this material in 3D printing applications. Now, how we can see this cross-linked network structure characteristic through our PYGCMS is what one is curious to know. Okay, so when you want to analyze this kind of samples, maybe the normal pyrolysis products may not be sufficient to interpret this data more kind of precisely. So we recommend to consider the reactive pyrolysis, where we use this tetramethyl ammonium hydroxide. When this photopolymer together with the cured resin is mixed with this TMAH, it leads to form different products. Okay, the methylated product that is coming from the methacrylate and also this dimethyl derivative of polyethylene glycol, also the methacrylate oligomers. So the methacrylate oligomers is the one that really tells you that this is a cross-linked networking structure. So if you look at this pyrogram, okay, so each of these methacrylate, monomer, dimer, trimer, and tetramer, pentamer, and so on. This really refer to the more number of cross linked network structure. So in other words, so if you look at this polymer, photopolymer, so the cured resin will have so many of these networking structures, and each of these, when I see a kind of hexamer, okay, yeah, this methacrylate hexamer refer to this kind of cross-link and network structure. So based on this pyrogram product distribution of the oligomers, one can really see how this photo initiator is helping to make this kind of photo cured resins. So you can optimize the dosage, also the choice of different photo initiator to really to make the preferred product for this 3D printing applications. Okay, in this case, yeah, basically we try to show the simple flash pyrolysis, but instead of flash pyrolysis, we do it as a reactive pyrolysis by adding tetramethyl ammonium hydroxide. The good thing in this PYGCMS workflow, you do not need to have a separate reaction time. Normally, when you do any of this methylation or FAME analysis, you have to add this methylating agent, then allow for the reaction. But since we are dealing with high temperature sample treatment, so this hydrolysis, reactive pyrolysis is taking place instantaneously. So it is like a one-step approach for you to really do this reactive pyrolysis analysis, which allow you to understand the like a cross-link network structure to really check the suitability or also the process performance of the different photo initiator that is mixed with the polymer. Okay, now I move on to the second part of my applications. I think previously Dr. Michael has shown about the UV radiator. That is something we have developed as an accessory, which allows to do the kind of online photo degradation of polymers. Okay. Now, the first question one may have, why we need this? If you look back, our traditional approach, people who are developing material for such external applications, or when they are exposed to light, sunlight, or other kind of forms of light, one has to look at its stability. So our traditional approach is basically put them on a rooftop for several months to several years and look at the degradation of the material. That is basically they try to do the integrity of the material at 0 hours versus several months and several years, and then they try to assess the stability. Now later on, people have started using this weather meter, which is actually much shorter than the traditional approach, but still it needs several weeks to several months. So when we do the weather meter, so they try to look at two things. One is when you expose the sample to the UV light or sunlight, then you try to analyze the volatiles that are being released, because the release of volatiles really define the stability of the material. Also, it can also reduce the molecular weight of the polymer, so that one can analyze the sample after a certain period of light exposure. Okay, so basically people wanted to do these two type of measurements. One is analyze the volatile that are released due to degradation during this light exposure, and also look at the material integrity after this. So both can be done with our PYGCMS, and by having this online micro UV radiator, you can do these experiments in much faster way, which will help you to accelerate your projects like kind of finalization, so that the products can be introduced to the market as early as possible. Okay, so in terms of the sample cup for this kind of application is not our standard deactivated cup. It has with some perforated holes, because when you expose the sample to the UV light, so it starts releasing some volatile. So with the help of these holes, they get released and sent to the GCMS system. But they are not really being separated. So we have this MJT, the cryo trap, so which will retain the compounds until this exposure time. Then we really start the analysis. The good thing is we can easily insert this UV probe with the optical kind of guide. Okay, so optical fiber which we use like a waveguide or the light guide, so we can expose the sample. And because as you know, for PYGCMS we take a very small amount of sample, so even for exposure we need very little amount of light. So this UV radiator allows to have the light intensity of like higher than like 60 millivolt at like 365, also like even like 700 millivolts per centimeter square of at this 280 to 480. Also we can adjust the intensity through a control, so that also will allow you to assess the sample at different intensity, at different kind of light intensity and the different wavelength. So this is the internal schematic of the sample cup, and also the optical the fiber, the UV probe. So it is important to have this gap, also the perforated holes that allows to release the volatile compounds and push it to the cryo trap, so where these compounds will be retained until the GCMS really starts. So the immediate kind of benefit compared to this traditional or weather meter is, you can see, so when we use our online system, okay, so without UV radiation, let's say the molecular weight is like 285,000. So after 1 hour, you can see the reduction to like down to like 240,000 and 3 hours. So, but the point is not about the reduction of molecular weight. So the data what we produce with just in 3 hours require 300 hours in weather meter kind of setup. So this is what we are trying to emphasize. Okay, by having this online UV micro UV radiator, you can really do this analysis or evaluation much faster compared to the traditional approach, whether it is with weather meter or even like the atmospheric the rooftop testing. So this is the key message that we are trying to put it first. Okay, use of online micro UV radiator with PY GCMS really help you to do this evaluation much faster way. Now, how it really helps in your real-time application. So I have three type of examples to really demonstrate that. The first example is we can study the evaluation of the weatherability of the acrylic coating of paints. Okay, as you know, when we are buying the exterior wall paints, we all want to have the longer lifespan because we do not want to spend money every other year. So usually now every company say our paint can last for 5 years or 10 years. How does it work? Basically, their formula or the formulation should have some UV absorber and also this light stabilizer that allows to retain the integrity of this acrylic coating paint, so that the lifespan of this paint can be extended to 5 years or 10 years depending upon the formula that they are selling. So now how we can use the PYGCMS to really study this kind of formula or paint, different paint. So here we have taken two type of sample. Okay, so one is just the acrylic coating paints without any UV absorber and this light stabilizer, and another one by blending these two UV absorber and light stabilizer. So as I have shown previously, when you expose the sample to the UV light, you will see a change in the peak shape and peak height. Okay, when they are being like degraded. So one of the key reason is the reduction of molecular weight. So you will see the reduction of peak, also the broadening of peak. So you can see the temperature difference starting from 35 up to 60. Okay, on the other hand, when the paint is mixed with UV absorber and light stabilizer, you do not see much difference. Okay, so that means our EGA analysis easily can like tell you whether this formula is working or not. Then based on the light dosage and duration, the exposure time, you can also look at the lifespan of the paint for such exterior coating applications. Okay, so EGA allow you to look at this information. This is one thing. Now, if you, as I said before, because our EGA data looks like TGA, but the data is coming out of the mass spectra. That means we always get this average mass spectra that can tell you some additional story to understand the mechanism or the nature of the material. So in this case, when you look at the average mass spectrum of this EGA, okay, so we can see this is actually for the sample B, where we wanted to see what changes is happening when the sample is, the formula or the mixer is blend is exposed to UV light. So we have used this light stabilizer as one of the additive, and that is actually when there is no light, we can see a prominent peak for this 138. But as we expose the sample to the UV light, you can see it is getting reduced and almost like disappeared. So that means when you have this additive into your paint, and when they are exposed to UV light or sunlight, so it absorb or it takes care of the light, so that the polymer integrity is maintained for certain period of like hours, that can be really extrapolated to number of years. So this is one way. Apart from just looking at the peak top temperature or the apex temperature and peak weight, you can also look at the average mass spectra and see what exactly happening. Then accordingly you can also change the dosage, as I said, because if you increase this dosage, it can last for longer hours also. So that's how you can optimize the formula of this UV absorber and light stabilizer, just looking at the EGA and particularly with the average mass spectrum. So now this slide basically again showing the comparison of our micro UV radiator data against the metal halide weather meter. So, okay, so in terms of the data, because it's actually calculated from the EGA, what I have shown. So we have just calculated the peak area, then see the reduction in peak area. So we can see that like in 5 hours and below, or like 5 hours or more, can easily like decompose or disintegrate the 65% of the polymer paint. Okay, but same data, it needs 2000 hours to get from the weather meter. So that is the benefit of using this online UV radiator compared to the weather meter in a laboratory setup. So again, the right side what you see is the sample with UV absorber. So as we expected, it is the degradation is less in this case, because the absorber and the light stabilizer is taking care of the UV light, so that the polymer integrity is maintained. So the two things we want to highlight from this data: one is the UV radiator with the PY-GCMS provides data much faster way than the traditional approach with the weather meter, and secondly, this data will allow you to understand the formula performance, whereby one can optimize the dosage or the composition of this UV absorber and metal stabilizer on different formula to really have a different grade of this exterior wall paintings formula. Now the example 2 is again looking at the use of this online micro UV with the PY-GCMS. So polystyrene, as you all know, it's very hot polymer but very fragile. So to really increase the impact, so people make this high impact polystyrene by blending polystyrene with butadiene. So where basically what happens is the polystyrene is bonded to this butadiene rubber backbone through this craft polymerization. So what we are trying to show here, how the PY-GCMS coupled to UV radiator can help you to again look at the integrity of these samples when they are like exposed to sunlight. Okay, so here we try to look at the UV PY GCMS data for virgin material and irradiation at 100 and 300 hours. I think when you look at this kind of, I think you would have seen this in many of the plastic wires at home or plastic material where you see some kind of decolorization. That is again showing some kind of decomposition of the polymer that is happening due to some oxidation as well as this photo degradation. Okay, so this slide I have shown previously also. So again, we want to highlight the benefit of using this online micro UV. So where you can get the data in 3 hours compared to what you required like 300 hours with the weather meter. So it clearly tell the reduction of molecular weight, and also you will see the shift of apex temperature, that the peak top temperature as you expose the sample to the longer duration of UV light. Okay, so this is one observation. Now, how does it affect my chemistry is something that we are interested to look at. So when you have butadiene, okay, as part of this high impact polystyrene, so the raw uh, high impact polystyrene will produce a prominent peak for butadiene monomer and dimer. Okay, now when you expose to the UV light of different duration like 100 hours and 300 hours, you can see the butadiene monomer and butadiene dimer peaks are totally disappearing. Okay, by the way, this sample is not during exposure. This is actually after exposure. So the material been exposed to UV light for a certain period, then the material being tested by PYGCMS through this flash pyrolysis. So what we are seeing from this data, right? When you have this high impact polystyrene exposed to sunlight, the decomposition is actually starting from this butadiene part, then going to the polystyrene where you see the reduction of molecular weight. So that means when this material is exposed to light, mainly it affects the butadiene. That means it will reduce its impact, the strength. Then it is only the polystyrene that will show only normal characteristic. So this UV light stability or the photo degradation can be easily studied with the help of this online UV radiator, and also the PYGCMS data allow us to understand the photo degradation mechanism. As I said, in this case, the high impact polystyrene, when they get exposed to the light, the degradation is happening at the butadiene rubber first before it's really start attacking the polystyrene. Okay, now this is the last application on this what's called the UV PYGCMS. So here I'm trying to show the application for this because the previous two data mostly we looked at the material analysis after UV light. So in this case, we wanted to show how one can really look at the degradation or the release of volatiles during light exposure. Okay, so when we have this polystyrene exposed to UV light for 3-hour irradiation, okay, what you see here is the evolved gases, okay, or like trapped with the help of our cryo trap MJT, then it undergoes the GCMS analysis, and this sample shows prominent peak for benzaldehyde, okay, and phenylethanol and acetone phenol. So this is on the gases that are released during light exposure. Then we also analyze the material after irradiation. As I said, usually we see the shift in the apex temperature, and also that indicates the reduction of molecular weight. Now, as I said, we can also understand the mechanism. So when we look at the possible kind of this decomposition mechanism of this thermal oxidation or thermal and oxidative atmosphere. So based on oxygen is definitely one thing, but if your air has got some humidity, that can also lead to form a difference. So if you look at these possible products, and when we compare our chromatogram that is obtained from this 3 hours UV radiation, we found the peak for benzaldehyde, phenylethanol, and acetone phenol. So that means it's very clearly showing that This is the pathway it is taking place. Okay, so it forms benzaldehyde, acetophenone, and because of the traces of water in the air, also shows the formation of phenyl ethanol. So particularly in this case, you can also calculate, okay, in terms of the amount of benzaldehyde formed and acetophenone formed, that can be related to the degradation of the polymer polystyrene film. So we can see there is a linear response. Okay, so when you have more number of hours exposure, then it is releasing more of benzaldehyde and acetophenone, which confirms the degradation hypothesis or the pathway uh, by which we are seeing the larger portion of benzaldehyde and acetophenone. Okay, so I think that's pretty much what I have from my side to share. So the key points, okay, from today whole session, PYGCMS can be seen as a powerful tool because it really expands the capability of GCMS and allows you to do the solid sample directly without any extraction. And you can also treat the sample at high temperature, and you can also manage the analysis with very little amount of sample, like less than zero point 0.1 milligram. It is widely used in different industry for QC, R&D, product failure, reverse engineering, and also processing. So processing again is part of the R&D work. And new areas like 3D printing also see the value of this PYGCMS for the 3D printing material characterization. As we have seen, because the PYGCMS just by itself can do certain things. Accessories like carrier gas selector, UV radiator, multifunctional spillage sampler, it expands its capabilities for more different kind of applications and objective. So that is the key message that we want to put it across. So thank you all for your kind attention. I pass it back to the chairperson. Yeah.
Thank you, Dr. Karthik. Very insightful talk on a lot of recent applications of PYGCMS, especially from the viewpoint of UV based analysis, UV radiation analysis and weathering, and also on something that is related to oxidative degradation. Because otherwise, we have been used to the fact that PYGCMS is mostly for pyrolysis related studies, but I think with the online UV and with the air ambience, it is also possible to do some oxidative degradation studies and understand the oxidative mechanism. Thank you for that. And let's also thank all the speakers of this session, all the three speakers of the session.